portuguesa, sou chileno, falo espanhol. Eu acho que é melhor se eu dou a aula em inglês. Tá bom para vocês? My subject is this. This is the main subject, Lovelock theory. This is a gravitational theory. In 4 dimensions or in higher dimensions, or actually in lower dimensions too. You can construct Lovelock theory in 3 dimensions. This is not general relativity, but it's based on the same principles. So it's very similar. And what's different is the field equations. But they're not so different. The equations, the field equations for the metric are of second order. And that's important because of tradition mainly. All differential equations, not all, but all main differential equations in physics are second order. Maxwell equations are second order. So you only need to specify the values of the field and the first derivatives as initial conditions to solve the equations. You don't need to specify higher derivatives at t equals 0. And so people often claim that second order equations are required to have a well-posed initial value formulation and to have causality. So you don't have problems with effects going before causes. That's more or less important. So that's going to be my subject in this. I think of it as 4 lectures. We're going to go till 5:30. We're going to make a break, half an hour break, and then we continue from 6 to, no, we break at 6. We continue from 6:30 to 8. And next Friday too. Well, what's the motivation for Lovelock theory? There are 2 kinds. One is from string theory. So string theory is this theory in 10 or 11 dimensions that needs to be compactified for dimensions to make sense for the real world. And when you compactify string theory, you end up with an effective theory of gravity. And this effective theory of gravity is expected to go beyond general relativity and to have in the Lagrangian higher powers of the curvature. The Lagrangian for general relativity.
And powers of what? The Lagrangian and powers of what?
Of the curvature. Higher powers of the curvature. the Einstein-Hilbert Lagrangian is this square root minus g times r. This is the Ricci scalar curvature. And string theory predicts that there should be corrections. And Lovelock theory provides this kind of corrections to general relativity in a very precise way. So that's one motivation. And the other one is this. Why not? Because actually the Lovelock Lagrangians have the same birthplace, or come with the same set of principles as general relativity. Okay, so what are those principles? In very simple terms, general covariance, all the equations of the theory are equations among tensors. They are the same in every coordinate system. So coordinates are not important. You can use any coordinates you like, and the physics doesn't change, doesn't feel like the difference. And the other principle we will care about is the equivalence principle that says that in a small enough region of space-time, you can go back to special relativity. You can dilute the effects of gravitation if you are in a small enough region. That's of course possible only locally, but it's locally possible everywhere. So that's the principle. By the way, if you need to stop me to ask a question, please do. You can do it in Portuguese if you want. I can try to understand. So the way general relativity is built is as a theory for the metric. That's the main character. And from the metric, you can build this symbol, which is called the Christoffel connection. And from the Christoffel connection, we build the Riemann tensor and the Ricci tensor and everything, and the Einstein field equations. So the first thing I'm going to do is I'm going to rewrite general relativity in a slightly different way, which is called the first order formalism. I'm going to do it because it's more convenient to do it in this formalism when you're dealing with Lovelock here. It's more simple, it's more transparent. So, what's this first order formalism all about? There are several ways to understand the metric, and one way is to think of it as the inner product of two vectors. So people sometimes write this. Have you seen this equation before? What's the idea behind this? You think of vectors in general relativity as this. These are the components of the vector, and this is the basis vector. So it's the same thing when you were studying mechanics some years ago and you write, I don't know, write this. These are the components and these are the basis vectors. So in general relativity, the coordinates that you choose in a small part of space-time provide a set of basis vectors, which are the partial derivatives. This basis is called the coordinate basis because it's the coordinates that define the direction in which you are taking the derivative. So for instance, if you have two vectors, you can take the inner product like this, and the components go out, and this product here is the metric. And you can actually write this in this way. So, are you familiar with this? Is this okay? So it's the same thing you do here. When you multiply two vectors, what happens here, this is 0, this is 0, and this is 1. So these vectors that we use in mechanics are very convenient. These are the coordinate bases for Cartesian coordinates, and they are convenient because the basis is orthonormal. That what it means is that this is 0 and this is 1. So if you compute this product, an orthonormal basis. The metric here is the identity. And that's okay because this is a flat space. This is a two-dimensional plane in which we are doing this operation with these vectors. So it's okay that the metric is the identity. But in general relativity, you usually have a curved spacetime. So the basis is not necessarily orthonormal, it's not even necessarily orthogonal. You may have things like this which are different from 0. And this happens because the metric doesn't need to be diagonal. So, any questions up to now? Is it okay? Well, but now the equivalence principle says that in every small patch of a space-time, you can go back to special relativity. In mathematical terms, what this means is that in every patch, you can find a basis of vector which is orthonormal. This is actually equivalent to taking the metric and diagonalize it. The same way we diagonalize any matrix. I'm going to introduce a new set of basis vector, a new basis that is going to be orthonormal. And I'm going to call it like this. And this is an index. I will use a time index that counts vectors. So this is really 4 vectors. And these vectors, I will demand that they be orthonormal. But in space-time, being orthonormal doesn't mean that the metric is the identity, because time is different. So orthonormal means that the metric will be the same metric as in the special relativity. And so this will be the Minkowski metric. Which is so it's not the identity, it has -1 to the corner. You cannot change the sign of that entry in the matrix. So if you go to a book about general relativity, it says that the metric is a 4 times 4 matrix which has 3 positive and 1 negative eigenvalue. Because when you diagonalize a matrix, the things that end up in the diagonal are the eigenvalues of the matrix. So these are the eigenvalues. And by definition of space-time, there's 1 negative, 3 positive. There's also a different convention having 3 negatives, 1 positive, but as far as I know, this is completely equivalent. You can choose whichever you want. And I choose this one. So we're going to make the transition. Well, these are vectors, and any vector can be written in a basis, in this basis, for instance. So we can write these vectors in the coordinate basis like this. And these here are numbers, these are the components of the vectors. You see? The same way, if I have a vector A, I can write this. Now I have not 1 vector, I have 4 vectors. These EAs. And every one of these I can write in the coordinate basis. And this here is like a change of basis matrix. It has two indices. It's a 4 times 4 matrix that changes from this basis to this basis. And of course, this matrix that changes basis from the coordinate basis to an orthonormal basis is a function of points. It depends on where you are, because the metric is different everywhere. So in every point, you need to perform a different change of basis to get the orthonormal basis. So this matrix depends on x. If it didn't depend on x, then space-time would be flat. Okay, now we said that this basis has to be orthonormal. Now, what does this mean for these guys here? I take these 4 vectors and I expand them in the coordinate basis, and I do the same with these other 4. And now I rearrange and this is symmetric. So the change of basis that we need has to satisfy this equation. This guarantees that the new basis is orthonormal. Okay. You follow me?
Sorry, I think I missed something. Like this, the EA doesn't depend on X itself, just change of basis matrix.
This actually
Yes.
also depends on x.
Also,
I didn't
so
write
all
down.
the dependence is included just in the change of base matrix.
Everything depends on x.
Okay.
Actually, the partial
Yeah, yes.
derivatives depend on how you define coordinates. But
I think that we can choose a matrix which cancels somehow the dependence.
that's the thing. Here, this depends on x, this depends on x, this depends on x, this doesn't. So that's the point. You are choosing a new basis such that the matrix locally is Minkowski. It doesn't depend on x anymore. And we're going to do this at every point in space-time. So every point in space-time, we're going to take the metric and diagonalize it and turn it into the Minkowski metric. And this is done through this change of basis matrix. And of course, this will be different at every point. Because at every point we have a different DB nu, and we need a different EA nu to diagonalize it. And the diagonal form of the metric is the same everywhere. That's what the equivalence principle says. That's Now, every change of basis to be permissible, to be acceptable, has to be inverted. We have to be able to go back to the original basis. No. Sorry. And this means that this matrix, the change of basis matrix, has to be inverted. And so the inverse, I'm going to call it like this with a bar, E bar. The index structure is inverted, and the fact that this is the inverse of this, what it means is two things. So it has to be the inverse on the left and on the right. Any matrix inverse does this. So if you take this E bar and multiply on the left, you are summing over the A index, and the result is the identity matrix, the Kronecker delta, in the mu indices. And if you multiply by the right, then you are summing on the mu index, and the result is the identity matrix on these AB indices. that okay? And so comes my first homework for you. The homework is to find the inverse, to compute the inverse, and to show that this E bar can be obtained from the E by changing the place of the indices. So you take the E, B, mu, and take this B index up using the Minkowski method, and you take the mu index down using the method. The result you write like this, and this is the inverse. This is the homework. You have to show this. You have to show that this guy here, defined in this way, satisfies both these equations. Is it clear? Do you have to show? Yes. It's not hard, it's an easy homework. Now we will go back to this equation here. And we are going to use the inverse to isolate the method. So we're going to multiply, let me see, by E A kappa E B lambda. This is the inverse. Notice how the indexes are placed. And what do we get here? So I started from here and I multiplied by this inverse matrix twice. And here I have this sum over A, and according to the definition of the inverse, this is delta mu kappa. Here I have a sum over B, again, the same reason, according to the definition of the inverse. This is delta mu lambda, G mu. So I'm going to use these deltas to change the indices here. And that's what I get. And if you allow me, I don't like kappa lambda so much. So I'm going to change this again to mu. So this is actually the the inverse equation to this one. Here you have the change of basis matrix acting on G mu to produce the Minkowski method. Here we are diagonalizing this space-time matrix. And here, through the inverse of this EA mu, we are going back. We are taking the Minkowski metric, and from the Minkowski metric, we are building the space-time metric G mu. Okay? But the inverse process, what I said here. You start with the coordinate basis, you go to the orthonormal basis, and you have to be able to come back. Otherwise, the change of basis is not permissible, not mathematically verified. So this is going to be an important equation for us. Because what it is, people like to read this equation this way. They have two e's here. So this is like e squared. And they have the metric here. And so they think, okay, g equals e squared. Quotes. So this e is like the square root of the metric. So people think of equation is nice because what it means is if I know this guy, then I can compute the metric using this equation. What it means is the following. If at every point in space-time I know how to go back from here to here, then this is equivalent to knowing the metric at every point. So the first thing about the first order formalism is that we are going to think of the metric not as the fundamental thing, but as a derived thing. And the fundamental guy we're going to think of this one. And we can do this because if we know this, we can compute it. It's as easy as that. So this is a change in point of view, but the content is the same. We're not changing the theory so far. And this is called the feedback. And this comes from German because Vier means four and Bein means leg. So this has 4 legs, 4 dimensions inside. So we can think of general relativity as a theory for the feedback. Sometimes they say feedback with an L because this field in German means many. So this is many legs, and this is nice for higher dimensions. So only 4 but many. Questions so far? Okay. Now, question for you. In 4 dimensions. It's a tensor, it has 2 indices, and it's symmetric. As we do interchange the indices, then the result is the same. So how many independent components there are? Count.
10.
10. Okay, that's right. 10 independent components because it's a matrix. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So it's a 4 by 4 matrix. So in principle, it has 16. But since it is symmetric, we can consider only this piece. And this is the same as this is the same as that. So it has only 10. And so the Einstein field equations somehow have to determine these 10 components. It's a bit more complicated than that, but in principle it works like this. So you need a field equation that will allow you to compute these 10 independent components of the network. Okay. Now we are going to change our focus from the metric to the field by. Now, same question. How many independent components does the feedback have? And the answer here is not 10. Because this is also a 4 times 4 matrix, but it's not symmetric. It needs not be symmetric. There's no way, actually, it has one index up and one index down, so you cannot really talk about symmetry when a tensor is written in this way. You can only talk about symmetry when both indices are down. So this is actually not necessarily symmetric, so it has 16. And that's kind of crazy because they are supposed to describe the same thing. They are supposed to have the same amount of information. And so it seems a bit crazy to go from one description that uses 10 independent components to another description that uses more, uses 16. What happens to the other 6?
The torsion. Perhaps the torsion.
It's related to the torsion, of course. In physics, this is not an unknown situation. For instance, if you take electromagnetism, you have the electric field and the magnetic field. Those are 6 components. 3 components for the electric field, 3 components for the magnetic field. But you know that you can derive the electric and the magnetic fields from the potentials. You have a scalar potential and a vector potential. Those are 4. So the same thing you can say with 6 components, you can say also with 4. And actually it can go down to 2. But there's a reason people like the electric field and the magnetic field, because they are related to the physics. They cause forces. They carry energy. And the thing is, in physics, many times it pays off. It's good to move to a description that includes more variables, but it has an increased symmetry. So that's what it means to go from 4 to 6 in electromagnetism. When you have 4 components, the potentials, you already kind of forgot about gauge invariance. You already used gauge invariance to introduce the potentials. So this difference here is because when we move from the metric to the field bank, we gain an extra symmetry. And that's what causing this difference, this mismatch. It's actually not so hard to understand. If you are in some points in space-time and you have a basis vectors that are anything, they are not orthonormal, they don't have 90 degrees angles, one is larger than the other, anything. And you use this change of basis to orthonormal. You have 90 degrees, they're very nice, like this. But this is not the only possibility. Because now that you have this, you can rotate this without changing this 90 degrees, without changing the sizes, and this is still orthonormal. So there's not a unique solution. There are many orthonormal bases you can choose for diagonalizing the metric. And you can choose any one of these, and the metric doesn't know the difference. So that's the symmetry. So now I'm going to be more precise about what I mean by this. It means that if I have this field line, then I'm going to rotate it. This is, I'm going to apply a transformation that will give me a new field line at E prime that is going to be a matrix times the old field. This is going to be the rotation. Okay? But this cannot be anything because we want this to still give us the same metric. So we want this equation to hold for the same metric given you as before. That's what it means to change the orthonormal basis without changing the metric. And so this condition here will restrict the kind of transformations we can apply to this field line. And what we get are these rotation matrices. So I'm going to replace here this transformation law with these equations. Okay, so they are replaced there. And now I'm going to rearrange things. So, but we know that this is the old field line. So this field line satisfies this equation. So if this is going to be consistent, then this here has to be I changed the indices, but it's the same thing. Wait, these are Lorentz transformations. So these rotations are rotations in 4-dimensional space-time that satisfy this, and they are called Lorentz transformations. If you recall, a 3-dimensional rotation it's made from an orthogonal matrix, a matrix that how is it called? The transpose times the matrix gives the identity. Lorentz transformation is similar. Instead of the identity, you have the Minkowski metric, but the rest is the same. So this is a content. If you take away the indices, what you have is this. Question for you. How many? You have to include the normal rotations in 3 dimensions. Those are 3 because you can rotate about every axis, x, y, z. And then you have the boosts, 6, which are 3 more in every direction. So in total there are 6. That's the difference. You have 16 here, and that's the 10 of the metric plus the 6. That's what causing this difference. Because we're going from here to here, we gain an extra symmetry, which is Lorentz transformations, and this is the 6 that gives the difference. This actually works in any dimension you want, and we said it before, but it can be done in higher dimensions. So, questions so far? I'm going to emphasize this. These transformations are local. So you can do a different local Lorentz transformation in every point. It doesn't have to be the same. Because here the metric doesn't know. So this lambda is actually a function of x. It's a local transformation that you can do. And so this is a local symmetry. You know, you have a field that is your physical field that will give you field equations, but you can do transformations, symmetry transformations that are local, that are independent at every point. This is called a gauge symmetry.
What's the detail?
Gauge actually means freezing.
It's frozen.
Yeah, it's very cold.
Do you want to ask it then to...
We will make a break in 15 minutes, so it's okay.
Okay. So in the break I ask
Yeah, that's
Here
the
you go.
next thing. Okay, is everything clear so far? Definition. I'm going to use this index mu to attach a dx mu, a differential. And I'm going to build a one form from this, from the field. It's actually not only one form, it's four one form. And this set of four one forms I'm going to regard as a Lorentz vector because that's the way it transforms. Ryan is too small here. So you see the local Lorentz transformation doesn't touch the new index. It only deals with the time indices. So I can attach a dx mu here, a dx mu there, and I have my transformation in terms of one form. This is not a coordinate transformation. Coordinates haven't been touched here. They're not involved. This is a gauge transformation.
What do you mean by the coordinates?
that when I change from this guy to this guy, I'm not changing the coordinates. I'm changing
The rotations and the boosts are where?
what?
And the Lorentz rotations and boosts are in what?
They are operating here on this index, on the index that counts the orthonormal vectors. It's a little bit like this.
The vectors depends on x, but
Yes.
each of them, altering each of them doesn't necessarily change x.
It's like, for instance, you can have E0, E1. They both depend on x. And you define E0 prime or E prime 0, E prime 1. This is just for you to do. You're defining new vectors which are a linear combination of the old vectors. But the coordinates haven't changed. This is a gauge transformation in electromagnetism, where you take the vector potential and you change it by adding or subtracting the gradient of a scalar function. Coordinates have not been touched here, but it's the same kind of transformation that I'm doing. Now, I'm not sure how familiar you are with differential forms. Have you worked with them? You know them?
One class.
Not much.
I try to teach in one class. But I think
Well, a differential form is a totally anti-symmetric tensor. this is the thing. A P-form is a thing that has components. And the components form a totally antisymmetric tensor with P indices. This is totally antisymmetric. These are the components, and these are the basis vectors. And the basis vectors are these differentials. And these differentials are multiplied with a wedge. In Spanish we say cuña. And now in Portuguese, product exterior, exterior product, yeah. But this form here is called cuña. Wedge. Actually, wedge means cuña. ¿Qué es usted?
No, because in Portuguese we don't have an explicit name for triangle without base.
And the nice thing about these P-forms is that you don't have to work with the components all the time. So you can multiply P-forms, we can take derivatives of P-forms without going into the details on the indices there. So if alpha is a P-form and beta is a Q-form, this has P indices, this has Q indices, and you interchange the order of the verbs. You get this? So there is a sign change only when both forms are odd, like 1 and 1, 1 and 3, 3 and 5. But when one of them is even, 2, 4, 6, 0, then there is no sign change. And you can take a derivative. This is a partial derivative here with a new index, but you have to anti-symmetrize over all the p plus 1 indices. And so this now is a p plus 1 form. And I'm going to leave you with one property of this exterior derivative. I will take a break. So when you apply the exterior derivative twice, it gives 0. Because you are anti-symmetrizing over 2 partial derivatives, but partial derivatives commute. So if you take mu and then mu and you subtract, that gives 0. So that's a nice thing. And there is also a Leibniz rule. If you take the exterior derivative of a wedge product of two differential forms, then you take the derivative of the first times the second without derivative plus the first without derivative times the derivative of the second, but there is a sign change. And it depends on which kind of form is the first one. Because you have to think of it as the exterior derivative has to jump over alpha p. So if you take like this and you interchange the order, this is a 1 form, this is a p form. So the root there, this is a 1 form because it increases the rank of the 4 by 1. So you can multiply differential forms. They satisfy this root. You can take derivatives. There are no second derivatives, only first. And there's a line screw. And that's all you need to